Good afternoon, everybody. So this work has been done by my master student, Aman Shukla. Unfortunately, he could not make to the conference because of visa issues. So I'm presenting on his behalf. So the motivation of the work lies here that during the planning or during the scheduling of the activities, there are several modes in which an activity can be performed. Choosing a mode can influence the time, cost, quality, safety, resource requirement of a project. And when there are several of these activities, to choose which mode the activity has to be done is a complex task. So, literature has suggested that the genetic algorithms can be used to understand which mode a particular activity should be performed. So, the first part of the work basically dealt with developing this framework with 7 objectives. And second part is, okay, now when the project starts and we find that there are some non-compliances with the schedule, how do we replan or reschedule our project so as to achieve its objectives? So these are the research questions, that what is the best mode for activities to start a project, and what should be done when the activities deviate from the planned solution during execution. So there is a limited objective scope. Primarily, the studies have focused on time and cost, and there is very limited integration with quality, maybe with safety risk, maybe some with environmental impact. And decision making is completely based on single Pareto solutions. And for the pre-plan and for the post-execution stage, there are not much studies. So these are some of the research objectives with which this study was carried out. That is to optimize time, quality, cost, safety, the resource movement on the genetic algorithms to find the best Pareto optimal solution using MCDM techniques. And with the technique that we used is Entropy-VIKOR, and to understand how the dynamic optimization can work out. So I will discuss about the formulation of our multi-objective optimization. The first is the first objective is to minimize the total project time. That is the time duration for all the activities on the critical path. Second is how to minimize the project completion cost, where the cost for every activity has been calculated. Then the third is trying to minimize the potential of rework using a particular activity. So here an quality index has been defined, and based on that index, the quantitative methods for every mode of the activity has been taken into consideration. Then we need to minimize the safety risk. We want the project to be safe, but every mode of the activity may not be equally safe. There may be a higher safety risk in some modes, and some modes may have a little lesser safety risk. So we are defining safety risk using our fuzzy logic, where we are defining the risk of severity using fuzzy numbers, and an illustration has been given how this has been done for different things. So we want the risk of labor injury, the risk of material wastage, and the risk of equipment failure we have taken into the calculation of ASR, that is the activity safety risk assessment. So this is one example how the safety risk assessment has been done for every activity. Then we move to project environmental impact, because we want to ensure that the mode that we are choosing should lead to lesser carbon dioxide emissions. So that is, so an LCA was performed to understand the total CO2 equivalent emission for every mode of that activity. Then the sixth criteria, that is, we want to even minimize the project resource movement. That yes, we want that because it is a crucial factor for a success of a foreign project to have balanced resource optimization at a project. So we have defined our PRM basically as a summation of the two moments of the resource allocation. That is the amount of the resource being used and the duration of the resource being used. So MX and MY, the two resource moments, take this into the consideration. So with this, we had about 6 of our objectives that we want to achieve: the minimum project completion time, the minimized project completion cost, maximum project quality index, minimum project safety risk, minimum project impact, environmental impact, and minimize project resource movement. So these are the 6 constraints that we will be dealing. So as a project, so this is what the proposed framework is. Now we will be using our genetic algorithm. The genetic algorithm will propose us Pareto optimal solutions. From the set of Pareto optimal solutions, we apply an MCDM technique, and based on that MCM technique, we will try to find out the best modes of performing every activity so that all these 6 objectives can be fulfilled. So this is one, and then we move to the dynamic reoptimization scheduling. That was the second part of the project. Only the framework we are just presenting here for that. So this is the results that we got from running our genetic algorithm. So we had about 25 activities, and each activity had various execution modes. So there were total about 53 million combinational possibilities. We went through the genetic algorithm. We found out 78 Pareto solution, and based on our Entropy-VIKOR solution, this is what we finally found, that which is the mode for every activity it should be performed so that all the 6 variables can be minimized. Sorry, they can be achieved, not minimized. And this is the final result. Now coming to the task that, okay, now the project is started. We are moving ahead, but there are some deviations in the initial 2 or 3 activities of the project. We measure that deviation, and now based on this deviation, do we need to now again reschedule, or we need to change the modes of the activities so that the objectives can remain the same? Has been tried out. So here what we are trying to do is we are trying to minimize the Euclidean distance for the change that will take place between the different activities. So this is so we are trying to collect the data from a real life project. So activity 1 and activity 2 has been completed. Activity 3 was partially completed, and it showed some deviations. So we measured those deviations and we ran into our algorithm, and this is what it showed, that activity 5, activity 8, 9, 14, 17, 20, and 23, the modes need to be changed so that the real objectives of the initial planning can be achieved. So in conclusion, the proposed framework integrates optimization, decision making, and project control in a single workflow. OBNSGA-III has not been widely used, but we tried to use it as an genetic algorithm for this problem, and it gave us good results. Entropy-VIKOR as an MCDM technique was applied, and dynamic reoptimization has successfully suggested an execution plan after the project deviation for the remaining activities. So the final takeaway is that construction optimization should focus on multi-objectives and should not end after just planning it. There has to be a re-optimization done again and again. So this is our authors, and thank you for any questions.